absolute value functions and transformations. We are going to look at absolute value functions with different shifts in them, and we've talked about parent graphs before. So these aspects here would be some form of shifts or stretches to the parent function. And it tells us the most basic absolute value function is a piecewise function given by the following rule. So if it is a positive number, then we use the value. And if it is a negative number, then we use the opposite. Right? If we plugged in -2, the absolute value of -2 is +2. It says that this function is sometimes called the parent absolute value function. Complete each step to graph this function. The absolute value of -3 is 3. The absolute value of -2 is 2. -1, 0, 1, 2, and 3. Now we plot these points on the graph using two arrays and connect them to display the absolute value function. All right, so we have -3, +3, -2, +2, -1, +1, 0, 0, 1, 1, 2, 2, and 3, 3. The vertex of an absolute value function is a single point where both rays have in common. So the vertex is this point at 0, 0. The domain of f of x equals the absolute value of x is all of the values we can put in for x. So if we looked at the function, we had for x was greater than or equal to 0, and for x is less than 0. This one goes to infinity. All numbers, we can put in decimals or fractions or irrational numbers. And this one goes out to -infinity. Numbers less than 0. We can go all the way out to the negatives forever. So to write the domain, we are going to use the bracket and parenthesis notation. So domain goes from -infinity to +infinity. Since we can't actually reach infinity, we use the parentheses, but if it was ending on a specific point, we would use those square brackets. The range is all the numbers that we would get out of the function. So even when we put in negative values, absolute value always changes them to positives. So our range goes from 0, 0 is the lowest we could get, to infinity. We can actually reach 0, so it gets that square bracket, but we can't reach infinity because it keeps on going, so we use that regular parenthesis. Our graph looks like this, and this point right here is at x equals 0. So it says, for what values of x is the function f of x equals the absolute value of x increasing? The function increases when it has like a positive upward slope or trend. So it's increasing from 0 to infinity. It continues on forever. But it's not increasing at 0 or decreasing at 0. It stops. That's like a turning point. So we're going to use that parenthesis instead of a bracket because 0 is not included in the section that's increasing. It's the turning point. So it increases from 0 to infinity. And again, we can't reach infinity, so we use that parenthesis. And it is decreasing from -infinity, so all the way out here, until you reach 0. but we don't actually get to 0 because that's the place where it turns around. So it's not decreasing at 0, it's just decreasing as it approaches 0 because it has that downward trend or that negative slope to it. You can compare the graphs of absolute value functions in the form g of x equals absolute value of x minus h plus k, where h and k are real numbers, with the graph of the parent function f of x equals absolute value of x to see how h and k affect the parent function. So we're going to determine if those h and k values are shifts either left and right or up and down, or if there's some form of a stretch. So it says, first create a table of the values for x and g of x. So you can see here they picked some x values, -6, -3, -1, and so on, and they've plugged them in. So let's see how they got those answers. We have absolute value of x plus 3 minus 5, and we're going to replace the x value with the numbers from the table. So they chose -6. -6 plus 3 is -3, but the absolute value of that turns out to be +3. And we have to subtract 5, giving us -2. And then if we were to swap it out with a different x value, let's try -3 this time. -3 plus 3 is 0, and the absolute value of 0 is still 0, and 0 minus 5 is -5. Let's attempt a positive one just to see how that would work out. If we replaced it with +1, 1 plus 3 is 4, the absolute value of 4 is 4, and 4 minus 5 is -1. Now we are going to graph, and it looks like they've done that piece for us. You can see this is the original parent function that we used in the first problem. And then they graphed the function g of x with those points there. So you can see that the vertex where it turns around has shifted down and to the left. You see this vertex went down and to the left. G of x equals the absolute value of x minus 4 plus 2. First create a table of values for x and g of x. If I plug in -5 minus 4 plus 2, this would end up with -9, and the absolute value would be +9. 9 plus 2 is 11. Then we'll try -3 minus 4. -3 minus 4 is -7. Absolute value turns it to +7, and 7 plus 2 is 9. -1 minus 4 is -5. The absolute value of -5 is 5, and 5 plus 2 is 7. 0 minus 4 is -4. The absolute value is 4, and 4 plus 2 is 6. One minus 4 is -3. The absolute value of -3 is 3, and 3 plus 2 is 5. 3 minus 4 is -1. The absolute value of -1 is 1, and 1 plus 2 is 3. 5 minus 4 is 1. 1 has an absolute value of 1, and 1 plus 2 is 3. This is the graph of f of x equals x, or the absolute value of x, the parent function. And this one is the graph of g of x, absolute value of x minus 4 plus 2. How is the graph of g of x related to the graph of the parent function? It is shifted four to the right and up 2. Where do you see the numbers 4 and 2 represented in the g of x function? Here and here. So if it's inside those absolute value bars, if you subtract 4, it's going to shift 4 to the right. And if you add 2, it's going to add or go up 2. So in general, how is the graph of the function g of x equals the absolute value of x minus h plus k related to the graph of f of x equals the absolute value of x? The parent function is shifted right h units. So if it was like 5, we would shift 5 units to the right, and k units up. So if it was k had a value of 7, we would shift that vertex up 7. Now, what would happen if h was a negative number? Like, let's say it said g of x equals x minus negative 2 plus 17. Instead of shifting right, we would have to shift it left because it would turn into x plus 2. And so it would shift left. This would still move up. If it was a negative 17, it would move down. Graph the absolute value function here along with the parent function. Again, the parent function has that vertex at 0, and the g of x function is here. You can see, since it's a positive, it shifted to the left. And it also shifted up 2. So we went up 2 and 1 to the left to get to that new spot for the vertex. Constructing functions for given graphs of absolute value functions. You can write an absolute value function from a graph of the function. Write an equation for each absolute value function whose graph is shown. It tells us h is the number of units that the parent function is translated horizontally, meaning left or right. For a translation to the right, h is a positive value. For a translation to the left, h is negative. In this situation, h is 2. You can see they shift to the right 2 spots. K is the number of units that the parent function is translated vertically, up or down. For translations up, k is positive, and for translations down, k is negative. In this situation, k is 3. They shifted up 3 units. So you can see that the function is g of x equals x minus 2, because h is 2, plus 3, because k was 3. Remember, we're using that function x minus h plus k. So we have that negative there. Even though h is positive, it's part of the function. B, H is the number of units that the parent function is translated horizontally. It appears that it is translated horizontally 1 unit to the right, so it is positive. K is the vertical change, and it looks like it was shifted up 3. So it would say x minus 1 plus 3. If the graph of an absolute value function is a translation of the graph of the parent function, explain how you can use the vertex of the translated graph to help you determine the equation for the function. Oops. We look at how many units the vertex is shifted horizontally for the H value and how much that vertex is shifted vertically to find the K value. Our turn, number 7. Remember, we're using that function x minus h plus k. This one is shifted 2 to the left, so that means h is negative 2, and it is shifted up 1, so k is positive 1, which means our function should say x minus negative 2 plus 1. What do we do when we see this in a function or an equation? That tells us we need to change it. And if you subtract a negative, that is the same thing as adding the opposite. It's not wrong to leave it as minus a negative, but it looks nicer and cleaner to change it to a plus or a positive. You can compare the graphs of absolute value functions in the form g of x equals a times the absolute value of x, where a is a real number, with the graph of the parent function, f of x equals the absolute value of x, to see how a affects the absolute value function. So we already looked at how h and k are vertical and horizontal shifts. Now we're going to see how this constant a impacts the parent function. So you can see here we have the parent function, and then they've graphed this function g of x down below. So by using a negative 2, it flips the graph upside down, and then it also changes how wide or skinny that function is. So it's a form of a stretch. We talked about shifts, now we look at the stretches and compressions. Then they have us graph 1/4 the absolute value of x. So we're going to start with putting that parent function on the graph. Starts at 0, has a slope of 1. So there's the parent function. If I plugged in 0 into this function, the absolute value is 0. 0 times 1/4 is still 0. If I put in 8, the absolute value of 8 is just 8, and 8 times 1/4 is 2. So we're going to go over to 8 and up to 2. How about if I put in negative 8? The absolute value of negative 8 is 8, and 1/4 of 8 is still 2. So we're going to go over to negative 8 and up to 2. So if we keep that a value positive, it still points up in the same direction, but it's not going to be the same because it's going to have a stretch or a compression piece to it. Describe how the graphs of g of x equals 1/4 of x and h of x, where it's -2 times the absolute value of x, compare with the parent function. Use either the word stretch or shrink and include the directions of movement. Well, g of x is a horizontal stretch. And we can tell because if we were to pull these endpoints here, or these two arrow pieces here, we would be stretching it left and right. So we say horizontal stretch. Then over here with the green one, if we took these two arrow pieces, we would have to put them closer together horizontally to get them to become skinnier or more compressed. So h of x is a horizontal shrink because we're pulling those two green points closer and closer together to get them to become skinnier and skinnier. What other transformation occurs when the value of a is a negative? When it's negative, it reflects the parent function over the x-axis. It flips it over. Graph each absolute value function. Let's choose to start with x value 0. The absolute value of 0 is 0, and -1/2 times 0 is just 0. I'm going to go by 2's because multiplying by 1/2 is easier when you have multiples of 2, but you can do 1's as well. So -1/2 times the absolute value of 2. Absolute value is 2 times -1/2. Well, half of 2 is 1, and then we make it negative, so it should be 2, -1 as our point. Now let's try 4. -1/2 times the absolute value of 4. The absolute value of 4 is 4. Half of 4 is 2, but we have -1/2 times 4, so it's going to be -2. Then we can do 6. We know the absolute value of 6 is going to be +6. Half of 6 is 3, but we have to make it negative. And then we can do 8 as well. -1/2 times 8 is going to be -4. So we have this line coming out this way. And then we also need to do the other side. The absolute value of -2 is +2, and +2 times -1/2 is going to be -1. Then we have -1/2 times the absolute value of -4. The absolute value of -4 is just 4, and -1/2 times 4 is -2. So you can see that it's going to start to take that similar shape on the other side. All right, now for 11. If I plug in 0, the absolute value of 0 is 0 times 4. 0 times 4 is just 0. If I plugged in 4, the absolute value of 4 is 4, and 4 times 4 is 16, so that's going to be way off our graph. How about 2? 4 times the absolute value of 2. Well, that would be 2. 4 times 2 is 8, so we're going to go over to 2 and up to 8. Then let's do -2. 4 times the absolute value of -2. Well, the absolute value of -2 is just 2, and 4 times 2 is 8. So we're going to go to -2 and up to 8. Why is it important to note both the direction and distance that a point is being translated, either horizontally or vertically? Well, the direction tells us if it's the h or k and whether it's negative or positive, right? If we're talking about h, a negative h would tell us to move to the left, and a positive h would tell us to the right. So direction indicates whether the value is for h or k and whether it's a negative or positive value. The distance tells us what numbers to use for h and k. If we move 2, then we would want the h or k value to be 2. If we moved 15, we need that value to be 15. How does knowing a point in the graph, other than the vertex, help you find the value of a? This helps us identify if the a value represents a stretch or a shrink. And if it's positive or negative. So we know if it's a stretch, a has to be between 0 and 1, and if it's a shrink, a has to be bigger than 1. Then we make it positive or negative based on whether it's above the x-axis or below. So it could be bigger than 1 in the sense of, okay, we're going to use 2, but then we make it negative and flip it upside down. Then it says, when graphing an absolute value function, how are g of x, which is a times the absolute value of x, and h of x, which is negative a times the absolute value of x, related? Those are reflections of each other. How would the graph of the parent function be affected if h is bigger than 0, k is less than 0, and a is greater than 1? If h is bigger than 0, that means it's going to shift to the right. Remember, positives are to the right, negatives are to the left. If k is less than 0, that is going to shift down because it's a negative number. And since a is greater than 1, it is going to be a shrink.